Hello, my name is Evan Shi. Thanks for coming to my talk. I'll be presenting a summary of the work done by an undergraduate team as part of the Opportunity Research Scholars Program at Georgia Tech over the last few years to develop low-cost ground stations for space solar power. This work was done as part of a propagation group at Georgia Tech, and our advisor is Dr. Gregory Durgan. The key challenge for implementation of space solar power is high power transfer over very long distances, such that the benefits outweigh the costs. For orbital distances, transmit and receive aperture areas must be on the order of several square kilometers, which is a ballpark result using the diffraction limit and safe power density levels. This allows us to increase our benefit, which is power generation, but it also increases cost dramatically. In fact, if we were to completely cover 4 square kilometers with a common RF substrate, just the substrate, no circuits printed on it at all, the cost for just the substrate by itself would be well over $1 billion US. In addition, that entire plot of land could not be used for anything else, practically speaking. If the substrate used were transparent instead, the land could also be used for terrestrial solar generation, or even basic agriculture, depending on how the station is actually designed. The goal of this project was to investigate lower cost substrates that could potentially trade efficiency and performance for a greater cost savings, to ultimately chip away at the massive cost that it would take to implement space solar power. We focused our attention on a few key areas: inkjet printing and using copper tape on low-cost transparent materials. So let's take a look at the two primary materials we investigated. Early on in the project, there had been a good deal of attention drawn to transparent, flexible circuits made using conductive inkjet printing on polyethylene. For example, the Athena lab at Georgia Tech does great work in this field. However, we wanted to investigate just how low the tolerances could go for this technology. We used a roughly $80 home printer and loaded it with self-centering conductive ink and printed out some RF circuits. The PET is cheap, light, and transparent, and the flexibility has the potential to be advantageous in installation. Here in this figure, we have a 3-stage RF to DC converter circuit using printed interdigitated capacitors and an LED load. The ink and PET combination was sourced from Mitsubishi paper mills, and the plastic sheets work. They have a thin coating layer that is used to absorb the ink and are quite thin, which leads to similarly thin traces during microstrip design. The substrate is fairly lossy compared to traditional RF substrates, and it only supports printing on one side because that's the side that the microporous coating is. This means that the ground plane for the microstrip transmission lines needs to be applied with a different material like copper tape. The ink itself is around 10 times less conductive than copper, which is still more than enough to classify it as a good conductor. But, as we will see later, the biggest flaw in this inkjet printing method is the thickness of the conductive layer, which is less than a micron thick. At 5.8 gigahertz in this material, the skin depth is several times deeper than the conductor, which leads to drastically increased ohmic loss. This, on top of the thin microstrip traces, leads to very poor efficiencies. Finally, conductive epoxy is used to affix discrete components to the circuit, like the diode package and the LED load. This epoxy is much less conductive than the silver ink and most likely contributes a significant amount of loss as well. It is also mixed and applied manually, which leads to inconsistent manufacturing and low prototype volumes. At scale, these issues must be addressed, but they could be solved using more expensive materials and printers and CNC plotters and such. Later on, we also investigated some common transparent substrates like untreated window glass and cast acrylic, also known as plexiglass. So for this, we used copper tape and used a laser cut stencil to trace out the circuit onto the substrate. This material is also much cheaper than fiberglass-based printed circuit board substrates like Rogers, or even FR4. The copper tape used is a layer of 1 ounce per foot, or around 300 grams per square meter, on top of a layer of conductive adhesive. The conductive epoxy is also used for this method to affix discrete components to the circuit. The substrates used were plain, untreated window glass and cast acrylic, which both have fairly wide ranges of dielectric constant and are most likely both anisotropic materials. However, our design philosophy, both with these materials and with the PET inkjet printing, was to design assuming that these non-idealities were not that bad, and then evaluate if the deviation from the expected performance is great enough to totally discount these materials outright. After all, we're not trying to design the best possible circuit at the time. We're just trying to prove that we could design a circuit on these non-ideal substrates. As well, we will see, while the circuits design might not match simulations precisely, they are still able to perform the task required of them. So let's take a look at the RF to DC conversion part of the Rectana circuit. The RF to DC conversion circuit we chose is a simple Dixon charge pump. The particular circuit in this case is not actually necessarily extremely important, because the goal of the project is to test viability, not necessarily optimize for best performance. However, some important observations can be made. First, many RF to DC conversion circuits choose components based on low power harvesting or scavenging environments, whereas a wireless power transfer environment should optimize for power levels several tens of dB above that. Therefore, PN diodes that suffer at low power levels may actually be preferred at high powers and can increase conversion efficiency. Second, it is not really worth it to save cost on discrete capacitors by using interdigitated capacitors. At some point during the manufacturing process, the nonlinear rectification device, the diode, has to be fixed to the substrate anyway. So avoiding the use of a few more discrete components is not saving much, especially since the substrates that we're using are so poorly controlled and can affect the values of the interdigitated capacitors. Using comparatively well characterized discrete capacitors reduces the sources of error in the design for little added cost. The final circuit design is based on work by Chung Tse, also from Georgia Tech. For high power levels, a single stage is better than multiple voltage doubling stages. Each additional stage adds parasitics, which are more costly power-wise, with higher currents caused by the higher received powers. The circuit is matched using stubs, but potentially could be matched using discrete capacitors in order to reduce the effect of the substrate even further. Next, we're going to address another glaring problem. The manufacturing techniques that we've mentioned so far both required a solid ground plane, which is obviously not transparent. This reduces the importance of the transparent substrate greatly. But if we can make the substrate transparent, we can use the land for something else, such as terrestrial solar generation. So there's a lot of incentive for us to try to do this. There's great potential for transparent conductors in this application. The following is based on work by Zachary Silva, also from Georgia Tech. In general, your two main types of transparent conductors are different types of transparent conductive oxides and meshed conductors. However, the big problem with transparent conductive oxides is that they suffer from thin conductive layers due to the manufacturing process, so you have higher resistances than meshed conductors. I would recommend taking a look at Zachary Silva's work if you are interested further, as he lays out the argument for mesh conductors in RF applications very well. For space solar power purposes, essentially, it means that we can aim to create almost totally transparent rectanas, not only meshing the ground plane, but the microstrip traces themselves using mesh conductors. And the primary reason mesh conductors are only recently being seriously considered is the significant amount of time a milling machine used to take to spend etching out all the tiny individual holes in the ground plane or the conductor. However, with laser etching and other microfabrication techniques becoming more common, mesh conductors are also becoming more and more feasible. Here we have a meshed 2.4 gigahertz patch antenna. This mesh is actually still quite opaque, but we can greatly improve this with more precise manufacturing. This was done by also by Zachary Silva. So let's take a look at what we've accomplished with the circuits that we made on these substrates. A few fully transparent loop antennas were designed using the inkjet printing on PET method, and they showed promising results for matching at 5.8 gigahertz. All the antenna designs were done in ANSYS HFSS, and all RF to DC converter design was done in Keysight ADS. However, the inkjet printing method was difficult to succeed with because the ohmic losses and substrate losses from the material itself caused the RF to DC converter portion of the inkjet printed rectanna to suffer greatly. Even with almost 20 dBm of power applied directly to the circuit, not applied to the antenna, the load LED barely turned on. The efficiency of the inkjet printing system was too low to be feasible using this particular manufacturing process. And we'll discuss alternatives in a little bit. But when we investigated copper tape on glass, we found that this method performed much better, and we were able to collect some good efficiency data. We found that the peak efficiency of 7.4% at an input power of 11 dBm and a loaded resistance of 300 ohms was fairly good. It's pretty low compared to the state-of-the-art rectannas, but again, we are using very low-cost substrates, and when we were evaluating our work, the circuit simulation during the design actually did not take into account the additional height of the conductive adhesive, which most likely adversely impacted the efficiency when this circuit was manufactured. The next iteration on cast acrylic instead of window glass focused on the goal of improving efficiency and experimenting with a meshed ground plane using a fine steel wire mesh. The antenna design was also improved. As you can see, we have a 2x1 patch array now. Unfortunately, all the undergraduates had to go home due to COVID before we could test the meshed ground plane rectanna efficiency, but the updated RF to DC converter efficiency simulation was very promising with up to almost 48% efficiency. While this would obviously be much lower when the circuit is manufactured and tested, our previous success using these low-cost materials is promising for the results of this circuit. So let's discuss some future steps and what we've learned from the project as a whole. Overall, inkjet printing suffered from many issues. The most important one was high ohmic losses, and this was inherent to the thin microstrip traces and ink layer that was thinner than the skin depth. We attempted to print thicker layers using our commercial off-the-shelf desktop printer, but the substrate was just not designed for it, and it didn't really work too well. So the way you could solve this is with a more expensive ink or a more expensive substrate that is designed for this sort of application, which would obviously drive up the cost. It's also difficult to apply a ground plane to this PET plastic, whether it's meshed or otherwise, because you can only print on one side, and so the other side, the ground plane, has to be attached either using copper tape, or you have to use another sheet of PET, and then the process of fixing those two sheets is not very easy, and probably leads to a lot of issues with air gaps and things like that. In addition, you have inconsistent adhesion of the discrete components, since these are very small components and they're being applied by hand. So all these issues can be addressed using more complex printers and materials and ink, but a more detailed look into what it would take to create feasible wireless power transfer circuits on this medium would be needed to make an informed cost-benefit decision. Finally, since the plastic sheets are not rigid, sagging, durability, and other mechanical concerns must be investigated for a true ground station solution using inkjet printing. Overall, copper tape on transparent substrates looks like a very promising path forward. There's much room for improvement in the design for the RF to DC converter, as well as in designing the transparent mesh. Also, using more advanced manufacturing techniques like laser to etching would most likely improve the performance by providing less rough conductors and better discrete component attachment. The key result of our work is that despite poor substrate characterization, we were able to get something that works on an exceptionally low cost substrate. Around 7% efficiency, improved with better manufacturing and design, is a great starting point for low cost ground station design. Further improvements to the transparency via mesh conductors can also still be made. Looking beyond, for an actual ground station implementation, other details still need to be worked out, such as weatherproofing the circuit with a radome layer. And finally, since implementation of space solar power is heavily tied to economics, economic analyses are needed. One basic requirement is looking at how much cost mesh conductors add to the bill. And more broadly speaking, an economic analysis is needed for what the total ground station cost or cost per area needs to be for space solar power to get off the ground. Once we have that coupled with the future improvements to the low-cost ground station technology that we've laid out here, this technology may finally reach the point where cost for the ground station is no longer prohibitive. Thanks for listening. Here's contact information for some of the teammates. Feel free to reach me at evanshi@gotech.edu. And thank you for coming to this presentation.